Good afternoon, everyone. Thanks for coming. Thanks, Zhilong, for giving me the opportunity to make a report here. Today, I'm talking about the 3D full waveform modeling and inversion of anelastic models. Okay. Why 3D full waveform modeling and inversion? First, because it can take account of the 3D small-scale heterogeneities in airs. So compared with seismogram calculated in a 1D model, the one calculated in a 3D model fit the data better. In the traditional inversion methods, they only use travel time or phase velocity information during the inversion. However, we can use both travel time and amplitude information for the full waveform inversion. Why we study seismic attenuation in airs? First, anelasticity is the intrinsic property of the airs. Here, the comparison of seismogram on the airs and on the moon shows that the seismogram on the moon decay very quickly, indicating strong attenuation on the airs. However, the lunar seismogram shows strong scattering and weak attenuation, which is mainly due to the lack of water. In the elastic model, the stress and the strain are linearly dependent, but the relationship in the anelastic model are non-linear. There will be energy loss when we propagate in the anelastic model. The red region shows the amount of energy lost to heat through the loading and unloading cycle. The intrinsic attenuation is measured by the quality factor Q, which is given by the formula where delta E is the energy loss per cycle, E is the total energy. So when Q is small, denotes the larger energy loss per cycle, indicating strong attenuation. When the attenuation is very strong, like we have Q equal to 10, the amplitude of seismogram decay very quickly. In the first part, I will talk about a new developed method for 3D full waveform modeling. In the presence of Q, the numerical modeling can be unstable if it is not well treated. For example, the instability problem arises in the forward modeling when some of the anelastic coefficients are negative in the viscoelastic system. To solve the problem, we optimize the anelastic coefficients in solving the anelastic wave equation. We also use an optimal strong stability preserving Runge-Kutta method, named the SSPRK in short, for the numerical modeling. Why the SSPRK method? The SSPRK method is popular for solving conservation law equation in fluid dynamics, which is widely used for the time discretization of semi-discrete hyperbolic PDEs. The figure shows the solution of the wave equation provided by the SSP and non-SSP time discretization method. We observe oscillations in the solution of the non-SSP time method. Moreover, the optimal SSPRK method is aimed at finding optimal coefficients to maximize the stability condition number. The rheological behaviors of the air's material can be simulated using viscoelastic or anelastic models. Two commonly used rheological models are equivalent. Here we just choose one of them, named the GMBEK, the generalized Maxwell body, which is a Hooke element collected in series with is a Hooke collected in parallel with a Maxwell body. This this figure shows the approximation of the Q factors using different number of mechanisms. The dashed line is the frequency independent Q factors, so it's a constant value, and the black line is the calculated Q factors, which is the sum of the Debye functions. So we can say when the number of mechanisms increases, the calculated attenuation factor approximates the exact value better. For an isotropic anelastic model, the equation of wave motion is governed by Newton's law, where ρ is density, v is velocity, sigma is stress, F is external force. The stress-strain relationship in the anelastic model is time-dependent, as here this formula, and sigma is stress. We'll have m mu is the unrelaxed modulus, which is the instantaneous elastic response of the viscoelastic material. YQ is the anelastic coefficient, and we can prove that the positivity of anelastic coefficients, that YQ larger or equal to 0, is a sufficient condition to obtain a stable viscoelastic system. And the JQ is the memorial variable, satisfies the first order ODE system. To solve the anelastic wave equation, we have unknowns, velocity, stress, and the memorial value. Then we write the anelastic wave equation in a compact matrix form. And we use the optimal M-stage SSPRK method for temporal discretization. It ensures the numerical discrete energy decay in time. For the spatial discretization, conventional SSPRK method usually uses a lower order finite difference scheme. Here we use a higher order, named the DRP, dispersion relationship preserving OPT McCormack scheme, which use the combinations of the forward and backward operations to reduce the inherent dispersion and dissipation in the numerical methods. Using the stability analyze, we get the current number alpha of the optimal SSPRK method and the classical RK method. So the current number is defined as the wave speed multiplied temporal grid size and divided by the spatial grid size. The table lists the current number of the two methods. We say that the current number of SSPRK method is larger than that of the RK method, especially for the 3D case. It means when the wave speed and the spatial grid size are fixed, we can use a larger time step for simulation in the SSPRK method, indicating an improvement in computational efficiency. We derived the numerical dispersion analysis of the classical Runge-Kutta method and the SSPRK method. We show the numerical dispersion area ER with respect to the number of grid points per wavelength G. ER is equal to like the numerical velocity, phase velocity divided by the real phase velocity minus 1. And as the number of grid points per wavelength increases, G increases, the areas is decreases for both methods. And if we set a threshold at 0.001, like the red line, we can say that the Runge-Kutta method lead like G larger than 6 point line, and the SSPRK needs like G larger than 5.4. So it means the SSPRK method could use a grid size 1.28 larger than that of the RK method. So in the 3D simulation, its computational time will be 50% less. To verify the accuracy of the SSPRK method in solving the anelastic wave equation, we design a homogeneous topographic anelastic model. This is the elevation and the distribution of the source and the receivers. We show the comparison of seismograms between the SSPRK method and the SEM method. We find a good match between the seismograms. We use the lambda of grid per minimum wavelength G equal to 18 in the simulation to accurate simulating of surface wave. The figure shows the phase misfit and amplitude misfit in seismograms of the X, Y, and Z directions at receiver 6 are calculated by the SSPRK and SEM methods. We can say the misfits are within 1% between the two methods, indicating the accuracy of our methods. We need to mention that the accurate solution provided by the SEM method is calculated in a region that is much larger than the SSPRK method. That is because there are reflections in the seismograms provided by SEM in the smaller region. That is due to the imperfection of the PML absorbing boundary condition. In contrast, the solution provided by the SSPRK method is stable and there are low reflections at long time evolution, even we reduce the QS as low as 5. We also use the LOH3 test, which is a benchmark test of numerical methods for modeling earthquake ground motion. Here is the model parameters for each layer. Here is the distribution of the source and the receivers. This figure shows the comparison of 3-component displacement seismogram at 3 receivers. We observe that the amplitude of seismogram decay gradually as the distance between the source and the receivers increases. The solution provided by the SSPRK and the SW4 methods match well. It verifies the accuracy of the SSPRK method for simulating ground motion in complex model. In addition, we compare seismogram at receiver R10 obtained by the SSPRK method and the quasi-analytical solution in the vertical direction. The misfits between the two methods are within 5 and within 2% below the reference frequency, while the amplitude misfit between the SW4 and the analytical solution are larger, within the 6%, even under the reference frequency. So this suggests an improvement of factor of 2 or 3 with the SSPRK method below the reference frequency, using the quasi-analytical solution as the reference. It verifies the improved accuracy of the SSPRK method for simulating ground motion in complex anelastic model. So for more details of the work, you could refer to this paper just published online. In the second part, we talk about 3D for waveform inversion. To date, the development of seismic attenuation models of the Earth has lagged behind those of the velocity models. One difficulty is in isolating waveform perturbation. For example, the waveform difference between the synthetic and the data could be due to anelasticity or elasticity. The anelasticity is due to intrinsic Q, and anelasticity is due to scattering, focusing, and defocusing. So usually it's hard to separate the effect of anelasticity and elasticity on seismograms. Another difficulty is due to different theories, like Ray theory, finite frequency theory, used to approximate sensitivity kernels. We propose that the joint inversion of velocity and attenuation parameter, that is the joint inversion of anelasticity and elasticity in a frame of four waveform inversion, will be helpful for solving the difficulties. In the reference domain, p-wave velocity of the isotropic anelastic model can be written as this. The logarithm term denotes the physical dispersion, which is related to the phase or arrival time on seismogram, and the complex form denotes the physical dispersion, and which is related with the amplitude in the seismogram. This figure shows the exact attenuation kernel and the physical dispersion Olin kernel, and here we get the difference between the two kernels. Below the difference, it cannot be ignored, because this is due to the 3D crystal heterogeneity. Thus, it is important to take account the effects of both physical dispersion and dissipation, named full attenuation. A joint inversion can incorporate the focusing and defocusing effects caused by heterogeneities. Based on the presentation theory, the perturbation of displacement of waveforms is expressed as an integral over the volume of the model, where delta U is the waveform perturbation, is the observed waveform minus the synthetic waveform, G is the string Green's tensor, delta rho is the perturbation in density, delta C is the perturbation in elastic tensor. According to the scattering integral method, the travel time anomaly delta T and amplitude anomaly delta A can be calculated through waveform cross-correlation as this, and we know that delta T is the average time shift of the waveform cross-correlation between the data and the synthetic seismogram, and delta A can be calculated as the log ratio of A over A tilde. A is the maximum amplitude of the cross-correlogram between data and the synthetic. A tilde A is the maximum amplitude of the autocorrelogram of the synthetic seismogram. So if we plug the formula of the displacement perturbation into the equation, we get the measurement of the travel time anomaly, and between the model perturbation that is collected by the sensitivity kernels. It means the measurements of the travel time anomaly can be linearly collected with the perturbation of the model parameters by sensitivity kernels. In the elastic model, the travel time anomaly can be calculated as this formula, where the alpha is p-wave velocity, beta is the s-wave velocity. While in the anelastic model, we need to add two terms, canceling the q factors of p-wave and s-wave. During the inversion, we use the parameterization of the inverse of qp and the inverse of qs. That is to accommodate the difference order of magnitude in the velocity and attenuation sensitivity kernels. we show the formula to calculate the travel time sensitivity color with respect to the QP factor. For each event, we perform one forward simulation from the source to receiver and save the string tensor. At each station, we perform one backward simulation from the receiver to source and save the string green tensor. So the color at each grid point in the media will be the convolution width of these two string green tensors. Of course, the J hat T is involved, where the J hat T is the Hilbert transform of the Zt. Gt is actually the normalized velocity.
I have a question.
Yeah,
I'm a
please.
little bit lost. Why do you need travel time sensitivity kernels if you're doing full waveform inversion?
Yeah, because even it is a full waveform, we extract the waveform, we extract the travel time difference, and we extract the amplitude information from the waveforms to do the inversion, and this will be our data.
So it's not a
Yeah.
real full waveform.
Yeah, it's not a direct comparison of waveform, but it's like it's kind of like because it's based on the scattering. It's based on the scattering integral method, and this method can like using the cross correlation type. So we will do the cross correlation of synthetic data and measure the time shift between the data and the synthetic. Also the amplitude difference between
Do you have to identify the phases?
Yeah, the phase is like the travel time. We are doing it in time domain.
Yeah.
Yeah.
But do you have to know the travel path? Do you have to identify the phase, like it's P versus double P versus?
We could select estimate the arrival time of different phases, and we could select the time window. But you could also do like it's for waveform inversion. You could simply select the time window. Yeah. So this figure shows the travel time and the amplitude sensitivity color of P wave with respect to the QP factor in a homogeneous isotropic anelastic model. We notice that the travel time sensitivity color look like the donut shape and has the minimum values along the rip path through the source and the receiver, while the amplitude sensitivity color has maximum values along the rip path. And the travel time sensitivity color is magnitude smaller than the amplitude sensitivity color, indicating the amplitude of seismogram will be more sensitive to the QP perturbation. For a numerical method to validate the accuracy of the sensitivity color, we can compare the measurements calculated from waveform cross-correlation as the measurement and compare the prediction calculated as the linear compilation of sensitivity colors. In a homogeneous anelastic model, we put a velocity heterogeneity perturbation in the rectangular region. We calculate the synthetic seismograms in the model with and without velocity heterogeneity. This is the source and the stations. At each station, we calculate the measurement of the amplitude anomaly on seismograms and compare it with the prediction. Overall, the measurements and prediction are fit and indicating the accuracy of the sensitivity colors. So finally, we apply our method to image anelastic structure in the upper mantle of Western United States, and we provide some preliminary results. The northern western U.S. has experienced a complex intraplate volcanism over the past 20 million years and formed several hotspot tracks like the Yellowstone hotspot track and Newberry hotspot track. The Yellowstone hotspot track moves follow the plate motion, while the Newberry hotspot track propagates in opposite direction. These different propagation directions make it difficult to explain the origin of the hotspot tracks. The hotspot tracks are thought to be the surface expression of the interaction among the southward moving North American plate, beyond upwelling mantle plume, and return flow introduced by the subducting oceanic plate down to the west. However, the details of the interaction and the hypotheses about the formation of the hotspot tracks remain undebatable. Imaging of seismic structure such as density, velocity, and attenuation in U.S. is important to enhance our knowledge of the origin of volcanic mechanism. Various elastic velocity model has revealed multi-scale heterogeneities, where we observe like the low velocities in the tectonic and the magmatic with very active regions, and we have relatively high velocities in the loss. However, there are only few regional scale Q reference models. Most of them, whether 1D or 3D, are at the global scale, which are smooth large-scale model. We plan to use the proposed 3D full waveform inversion method to image both velocity and elastic structures in the upmantle of the western U.S. The U.S. area transportable area provides unparalleled seismic data, allowing for high-resolution imaging across U.S. We will incorporate waveforms of body waves and surface waves from the networks to improve the lateral and vertical resolution in the model. The joint inversion will facilitate the exploration of the upper mantle structure in the western U.S. and help explore the complex interactions of mantle upwelling with asthenosphere and lithosphere. For an event, we compute synthetic seismogram at different stations generated in the reference model with and without attenuation. We find that the seismograms calculated in the model with attenuation fit the data better in both the travel time and the amplitude. And from the histograms for measured travel time and amplitude at all stations for the events, we find that when Q is added, the mean value moves toward to 0 and the variance also reduced. So it means it is important to incorporate attenuation in seismic tomography. Here we show an example of the sensitivity colors. The event locates at the Blanca transform fault, and we show the seismogram at one station. Here we observe the synthetic seismogram actually fit the data relatively good in the travel time, but now some difference in the amplitude. We show the horizontal and vertical amplitude sensitivity color with respect to the QS parameter. The sensitivity color has large positive in the color blue along the ray path. That, like if we put a small Q perturbation in the ray path and that will produce a positive velocity, a positive parameter perturbation, since the 1 over q becomes larger. And then we have the Carroll positive model perturbation positive. We will get a positive perturbation on the measurements. So that means the amplitude of the data will become smaller when we add the low Q perturbation in the repass. And we also show the differential horizontal sensitivity colors at 2 stations. Differential sensitivity colors will reduce the effect of uncertainties in the source terms and mainly provide information about the structures near the 2 receivers close to each other. The differential sensitivity colors are not fully cancelled out in the fallow zone, they indicating the 3D heterogeneities along the way, as well the difference between the 1D ray-based sensitivity colors and the 3D finite frequency-based sensitivity colors. The inverse problem is equivalent to solve the linear least square problem. We apply the standard LSQR routing with the constant regularization parameter for the inversion. For example, for the travel time anomaly delta t, we will have the minimize this wave equation where we introduce the weighting parameter W, the smoothing parameter, and the smoothing matrix. And here we also introduce the damping factor. And the delta as solution X will be the model perturbation. Here we have the travel time anomaly. The amplitude anomaly could be written similarly. We plan to combine the travel time and amplitude information during the full waveform inversion. For the travel time only inversion, we will have this equation where A delta t contains the travel time sensitivity colors, X the model perturbation, B delta t is the travel time measurements, and for the amplitude inversion only, we will have this formula where A delta A contains the amplitude sensitivity color, X the model perturbation, and B delta A is the amplitude measurements. So there are 2 problems if we want to adjoint the travel time and amplitude inversion. First, because the travel time measurements in the unit of second, but the delta A is dimensionless. So we will do a weighting parameter, usually could take 1 over standard deviation of the travel time anomaly to eliminate the unit difference of the 2 types of the data. And we also need to have another weighting parameter to balance the order of magnitude of 2 types of the sensitivity colors. We need to note that the solution is still unchanged even we do the weighting of the 2 equations. So to start with, we choose a small number of events and only TA stations for the inversion. However, we still have a relatively good repass coverage for the source and station pairs for the first iteration. We choose the surface with data and compute the travel time and amplitude anomalies at different stations. As an example, for the event in the California, we show the travel time measurements, and we can see here around the Newberry hotspot track we have smaller travel time difference within the 4 seconds, but we have some large values around the Yellowstone hotspot track. This is similar in the amplitude measurements. This indicates the structure near the Newberry hotspot track is better resolved in the reference model. Here we show the reference S-wave velocity and its perturbation at a depth of 80 km for the first iteration. The reference model is taken from this work, where we observe the relative low velocities beneath the beneath the back arc regions. However, the velocity perturbation is very small after the first iteration, and we think meaning two reasons. The first is that the reference model is already very accurate based on the seismogram at different stations, and also means the inverted model needs to be improved.
Now, can you go back to the previous slide?
Yeah.
I'm just wondering, what do they use to get this kind of reference model? What kind of information they use?
So this model is taken from this work, where it used the receiver function, surface wave dispersion, and also the gravity adjoint inversion. Yeah. And here we show the reference QS factors, and it's taken from this work, and the Q perturbations at depth 80 km for the first iteration. We observed the relatively low Q perturbation beneath the back arc region. Since we use the sparse distribution of stations and we use few events to the stage, we cannot resolve the detailed structure along the hotspot tracks very well. We think more iterations will be followed and more data will be added later. So we developed the SSPRK method for the 3D modeling and inversion of the anelastic model, and we verify its accuracy using synthetic tests. We apply it to image anelastic structures in the upper mantle of the western US, and the results will be improved and validated further. We expect our tomographic model will have better constraints on velocity, attenuation, and temperature due to the joint inversion of anelastic velocity and attenuation. So here is the take-home message. Please explore the computational efficiency of the SSPRK method when compared with other methods, such as the spectral element method, the SW4 method, and check how the large current number will improve the computational efficiency, like in terms of the computational time per time step or the total computational time. Also check the effectiveness of the implementation of the absorbing boundary and free surface boundary conditions, how they will help to improve the computational efficiency. And also think about whether our method or tomographic model will be helpful to your research. Yeah. Thanks for attention. I'd like to take questions.
Thank you very much, everyone. So thanks for giving us such a great talk. Anybody have any questions? I think we have plenty of time.
You have a really interesting method. So what, do you apply the same damping and smoothing to both of your types of parameters in your inversion?
Yeah, that's a good question, and I think there are many details during the waveform inversion. So at this stage, we will mention that for the smoothing, that is to balance the matrix in the A matrix, like different sensitivity colors. So for that smoothing factor, we will use different kind like smoothing parameters. But for the damping parameter, that is to have an effect on the model perturbation parameters. At the current stage, we are using the same damping parameters for all the model perturbation, but we are doing more analyses, and we expect to use more different damping factors that will give a balance on the perturbation of velocity and attenuation structures. Yeah. Yeah.
So you didn't consider the density variation in your inversion?
For the forward modeling, we have the density in our model, but for the inversion, the density model is not iterated. It's like the same as the reference model. Of course, we could incorporate density inversion later, and next one, my colleagues also do some implementation of density using the elastic medium as the first initiative. Yeah.
But the amplitude should have some sensitivity to density inversion. So
yeah.
You're not using some relationship between P and density.
Yes. Yes, usually the density could be like has some different type of empirical equations to calculate it based on the VP or VS. And for our model, because we use the density model from the other works. And in that work, because they use the gravity data, and we suppose the density is already well resolved. But yeah, I agree. We will improve the density later. That's a good idea. Yeah.
My second question is, you have from the travel time, you have 8 seconds, not 5 seconds. But for the immersion result, you only have a few meters per second change.
Yeah. Yes. Because as you can see here, for the travel time difference, we have a mean value of about 3 seconds. So that will be like if you assume from the source to receiver like 10 degree, and assume the reference velocity of 4. That will give you a velocity perturbation about 1%. But during the inversion, we did notice we have very small velocity perturbation, much less than 1%. So we could only say we have two reasons. Yeah, we don't know the exact reason, but I think more research needs to be done.
Did you look at the data feeding, the waveform feeding?
Yes. I haven't yet. But if you check the reference, if you check the seismogram comparison between the starting model, actually it's already have a good fit in the arrival time, and there is some difference in the amplitude difference. Yeah.
So I have 2 questions. First one is follow-up question. So I think you are inverting for multiple parameters, and velocity and attenuation, for example, they know to be crosstalk each other. Do you see a crosstalk in your inversion method, or during your inversion, or how do you handle the different parameters and how they talk and crosstalk between your parameters? That's the first question. And the second question is, can you comment on how you calculate adjunct modeling? Because I think you want to put negative Q, or how do you calculate, then how the stability goes, how the computational stability of the adjunct computation.
Let me ask first question. So it's the first question is about how I can cumulate the different parameters, like velocity and Q parameters. Am I right? Yeah.
So how they usually talk each other? So they have when you do the velocity attenuation inversion, they tend to contaminate each other.
Yeah. So basically, it's very hard to separate the effect of velocity and attenuation. So that's why we propose that we will use the joint inversion. Like one time we will invert 4 parameters. like as a combined effect, so that theoretically that won't give you a bias on either side. But during the implementation and also based on the analysis of the inversion results, I have to admit that there will be many issues related, because first we know the like the perturbations of velocity and also perturbation of the Q parameters are at different scales. And also we have different scales in the sensitivity kernels. And this all give us the challenge to do the modeling and do the inverse problem. Yeah, I think that is really a problem we are going to solve better and better. Yeah. And for your second question, it's about how I do the Q in forward modeling or in adjoint. So it's in, you mean the adjoint inversion?
Yeah, you need to backpropagate, right?
So because we use the scattering integral method for the full waveform inversion, and in this book, and then they have proved that the scattering integral method actually theoretically is equivalent to the adjoint inversion method. So theoretically they are equivalent, but they have different steps when performing the inversion. And for the scattering integral method, that is, we need to save the string green tensor at every grade and at different time step. So basically, we need lots of disk to computational storage to do our work. Like when I do the simulation here, I use a smaller number of events and stations. It takes about 3T on our cluster, and so that's why we know we have few attenuation model, and most of them is at the global scale. Yeah. But then there is some advantage for the scattering integral method or saving the string green tensor. For example, when we do the source locating, and if we save the green tensor, then the waveform will be the string green tensor convolve with the moment tensor, and we get a displacement. And so it means you get the displacement at one station. You only need to compute once. And but if you do the forward simulation, you need to, when you do the so for the like yeah. So when you do the source, when you do the source location, inversion, and you save the string green tensor, and displacement will be the string green tensor convolve with the moment tensor. So if you estimate a moment tensor for each possible sources, you could directly get the seismogram from the source. This is all possible source regions. This is all the possible sources, and this is the stations. So for one possible source, you only need to do one simulation, get the seismograms in the station. So, and but if you do the direct search, you need to put different sources at a different location and get the synthetic seismogram at the stations, and that will be thousands times of the simulations. If you save the string group tensor, you only need to do one simulation to get the seismograms at all stations. And I think some like South California Center, they also have some like they save the string group tensor for the spatial use. Yeah.
Questions?
Yeah, another question.
Yeah.
For your Western US model, are your events all located within your model grid?
My events?
Yeah.
You mean my events is yeah.
Okay, so that's all, you account for all of the structure between the event and station within your inversion?
Yes. Yeah, so this will be my whole computational region. Yeah.
But it seems that your reference model doesn't have you have only the station on land, right? In the reference model.
Yeah. Now I mainly use the stations. Use the TA stations, and it's mainly on the land. Yeah, I don't have. I don't use the OBS data yet. Yeah.
So I have a question.
Yeah.
So how do you compute the string tensor?
String group tensor.
Yes, string group. You need to compute the backward wave field to compute.
The string group tensor actually is a little bit complex. So theoretically, it's like it's the like the partial like the string group tensor is like it acts as you put a source at you put a pulse source you put a pulse source in the medium, and we will generate waveform displacement, and basically that waveform displacement will be the string group tensor.
So you need to compute the wave field.
Yeah, actually the string tensor is kind of like the gradient or compilation second partial derivative of the displacement. Yeah,
While computing it, you need to solve a wave equation and the backward wave equation.
Oh, it's actually it's kind of like a backward simulation, but actually it's not. You use a minus t during the simulation. It's just you put the source at your receiver. So we say that is like a backward.
So, and you don't need to change the sign of your Q vector.
Yeah, I don't need to do that. The model is the same.
So it will not affect the stability while computing, for instance.
Yeah.
Any more questions? So I think that's it. Let's thank Dr. Wang for